So that's the idea of a decision tree for classification. Now we need to actually come up with a way to learn this decision tree from data. And the most common way is to use something called a greedy algorithm, and that's what we'll discuss today. So this is an algorithm where we basically follow the same sequence of events from the previous slides. We start with one node, and then we would decide to split that one node into two children, and we have to make a decision how to split it. And then given that split, we have to now decide to take a leaf node and split it into two more children. So for example, we would evaluate both leaves, see which one would be the best to split, and we would make this split. So we grow the tree from nothing to something. First, let's briefly consider learning a regression tree. So imagine that we have 5 regions. What does our regression function look like? We take an input x, we evaluate the function of x, which is now going to be equal to this sum, where we take the prediction for a particular region M, multiply by an indicator whether x falls in region M, and then sum over all the regions. So this indicator will be true only for the region in which x falls, which will then pick out the correct prediction, Cm. Imagine that we had this partition of these regions, and we wanted to find the optimal values of each Cm. How do we do this? So the way that first thing we have to do is set up some sort of an objective function. And for regression trees, the default objective function is going to be the sum of squared errors. So we take, for each data point, the true output, which is a real valued number, minus the predicted output, square it, and sum it. So this regression function, conditioned on the partition, is simply going to break down into m different problems based on which region we're considering. So if we want to learn Cm for corresponding region Rm, we're summing the sum of the squared errors for all of the data restricted to their falling in that region Rm. And so it's straightforward to show that to find the optimal Cm, we simply average the corresponding outputs for all of the data that are in that same region. So we look at all of the data, we say which of those data points fall in region Rm. We then take their corresponding outputs, y, in the training set, and then average over those outputs. That's how we can minimize the sum of squared errors. So more complicated is finding these regions to begin with. Given the regions, we can simply take all of the outputs corresponding to the data in a particular region and average them. That minimizes the sum of squared errors. But how do we actually find these regions? So let's consider that we have a particular partition like this. What we would do is simply look at each region. So it's really just a brute force method. We look individually at each region. We look at each dimension for all of the data in a particular region and decide what's the benefit we can get by splitting along that point. So for example, if we look at all the data in region R1, we can then split it along either the first dimension or the second dimension. So we literally take R1 and evaluate all possible points at which we can split it along each dimension and say, what would the result be? How much would I reduce my objective function, the sum of squared errors, if I did that? So let's consider splitting a particular region R at the dimension j, along the dimension j at a particular value s. So for example, if R is this region here, we look at the first or second dimensions, so j equals 1 or 2, and then split it at a particular value along those 2 dimensions. We then have a proposed dimension j and a proposed value s for a particular region R. We then say, how would this partition the data in region R? So we construct a set R minus, which is all of the data that's in region R, such that the jth dimension is less than s. So we say the resulting partition would put all of the data in region R into either the negative group or the positive group, depending on the value in the jth dimension and how it compares with s. We then update the proposed prediction, so the proposed value for C, if we made that split, and we look at how much would we reduce the resulting objective, minimize the sum of squared errors. So we do this for every single region, we do it for every single dimension in each region, and we do it for all the possible splitting points S that would lead to unique subsets, a unique partition. And we can, for each of those proposals, get a new possible regression function f, and we evaluate each of them. So it literally is a brute force method. The computer can do it very fast, but it's literally just checking every single possible split we can make and picking the best one, the one that minimizes the sum of squared errors the most. For classification, it's a bit more complex because we need to somehow measure how good a region is performing. With regression, we can look at the sum of the squared errors for all the predictions that are made for all data in a particular region. For classification, we don't have a natural measure of performance. So there are three measures that we can possibly use. One of them, so what we will do is for the k-class problem, we have k classes. We're going to look at all data in a particular region, call it Rm, and let pk be the empirical fraction of the data that have label k in the region Rm. So we look at a particular region Rm and we construct an empirical distribution on the labels for only the data that fall in that region. Then to measure the quality of our prediction, because remember our prediction for a particular region is just the most prevalent label. We predict the most probable label. The measure of the quality then for that prediction could be either the classification error, so 1 minus the maximum of pk. So if pk, if for a particular k, the maximum of pk is the most prevalent label in that region. So we won't get that one wrong, but we'll get 1 minus pk. We'll get that fraction wrong. So that's the classification error. We can also use the Gini index, which is 1 minus the sum of squares of pk, or the entropy, which is this term. So each of these is going to be maximized or large when pk is uniform, when we are completely uncertain about what the label could be for that region. We have equal number of all the labels in a particular region. We maximize these things. Of course, we're trying to minimize them, so when they're minimized, all of the data in a particular region just falls into one class. That's when all three of these are minimized in those cases, and they're all equal to 0. So let's look at an example for growing a classification tree. Imagine that we have this current setting. We have region 1 and region 2, and we now want to decide which of these regions to split, and along which dimension to split it, and where to split it. Our current tree looks like this. Our current tree says take the first dimension, and if it's less than 1.7, go to the left and declare class 1. If the value in the first dimension is greater than 1.7, go to the right of the decision tree and declare class 3, which is class 3 is the most prominent class in this region. Class 1 is the most prominent in this region. Now we have two possible regions that we could split. We could split this region along either the first dimension, so we could either put another line here, or along the second dimension and put a line here. Or we could split this region along this dimension, meaning put a line here, or along the second dimension, put a line somewhere along here. We have to decide which one of these regions to split, where to split it, and along what dimension. So first notice that this first region classifies class 1 perfectly. So we're not going to improve the objective function, whatever we choose the objective function to be. We're not going to improve it by splitting this at all. So for the objective, let's look at the Gini coefficient, just to pick one. And let's look at splitting this second region. So currently, this region has a Gini coefficient, so that's what this is indicating. U of R2 has a Gini coefficient equal to 1 minus the sum of the probabilities of each class in this region. So there's 1 over 101, so there's the entire data set in this region is 101 points. There's one class 1, so we have 1 over 101 squared minus 50 over 101 minus 50 over 101, both squared. So there's 50 of the blue points and 50 of the green points, and there's a total of 101 points in this second region. So we have a Gini coefficient of 0.5098. We want to now pick a dimension to split and a point at which to split to minimize the resulting Gini coefficient of the two regions. So what does that mean? What is the improvement that we get from a split? Well, we have our first Gini coefficient from the original region. We then choose to split this region into two different regions. So call one of them Rm minus and one of them Rm plus. For example, if this was where we split, then this region would be Rm minus and this region would be Rm plus. We calculate the Gini coefficient for the resulting data in those two regions, like this, and we multiply it by the fraction of the data that fall in those two regions. And so this is the result that we would get. This is the Gini coefficient that we would get for a particular split. We look at the difference, and now we want to minimize this thing. So let's actually check both dimensions at all of the possible points for this particular region. So what this plot is showing is for the first dimension, so that's this dimension, split it at a particular value for t. So for example, if you split it here at 2, you would get this region. So if you split it here at 2, you would get this partition. You would have all of the data following in this region in R2 minus, all of the data in this region in R2 plus. And then let's check the reduction of the Gini coefficient for that point. So we get this value. So we see that the reduction as a function of t, so t here can be roughly 1.7 up to roughly 3. So that's what these possible values correspond to these values here. At a particular split, we get the reduction value, and we look at so this is absolute value of the reduction. We look at the largest value. So for example, right here at about 2.25, so let's say right here, corresponds to the best split if we were to split along this first dimension. So the best split for this first dimension is right about here. And we get that magnitude of a reduction. Now we look at the next dimension. We look at the second dimension and split it values between 2 and say roughly 4.5, which is where the data, there's no data above 4.5, so we don't have to check up here. So we check at that interval between about 2 and 4.5, and we propose splitting at each of those points and see how do we reduce the objective function or the Gini coefficient as a result of a particular split. And we suddenly see that at this point here, which corresponds to roughly this point here, we get a reduction of 0.25. And if we look at the maximum for the previous dimension, it was less than 0.02. So the reduction we're getting by looking in this second dimension is massive compared to the reduction from the previous one. So the previous one was maximized at about this point. We're getting a huge reduction in the resulting Gini coefficient, and that's intuitively just says that this split makes us much more confident about the two classes in each of the resulting regions. So that's where we then decide to take the second dimension and split at this particular point for this particular region. So it's very brute force. It's not elegant by any stretch of the imagination, but that's what the algorithm does, and of course computers can do this extremely fast. So one thing that we've sidestepped is when do we stop growing this tree? When do we stop splitting regions? And the amount of uncertainty that we get, the reduction of the uncertainty is not a good way to decide this. So for example, look at this setting where we have these points are in class 1 and these points are in class 2. Any particular partition that we make is not going to give us any reduction of the uncertainty. No matter where we split, where we split to make this first one region into two different regions, we're not reducing our uncertainty. In all splits that we can make, we have the same amount of class 1 and class 2 in both splits. However, if we could make our regions split this way, suddenly we perfectly predict. So uncertainty reduction is not the way to do it. In practice, what is done is that the trees are overgrown, so we make many more splits than are possibly necessary to get many, many regions, and then we prune the trees back using an algorithm. So this algorithm is not something that we're going to discuss in this course. It's not a trivial algorithm, but that's what's done in practice. We grow out the tree much bigger than we need it to be, and then we run an algorithm to prune back some of the branches in order to get a good tree. Another problem with these regression and classification trees is the idea of overfitting. So if we grow a tree out too big, we can eventually partition the input space into enough regions where we perfectly classify or perfectly predict everything. However, we get this type of a situation where the number of nodes in the trees, if we increase it, reduces the training error continually, but the testing error on a held out set at some point starts to get worse and worse. So we always, in a certain regime, we're improving our testing error, but then at a certain point, our trees become too complex and we start to overfit to the training data, and we get worse and worse testing predictions because it doesn't generalize to new data as well.